In our second example today, we want to look at how we can use the calorimetry equation in a new context to determine the specific heat of a metal sample if we know the mass of the sample, the heat taken in by the sample, and the change in the sample's temperature. This corresponds to worked example 9.2 in the OpenStax textbook, and this is the setup for the problem. We have a piece of an unknown metal weighing 348 grams. When the metal piece absorbs 6.64 kilojoules of heat, its temperature increases from 22.4 degrees Celsius to 43.6 degrees Celsius. We would like to determine the specific heat of the metal sample. And the idea is, in context, much like density, the specific heat of a pure metal is relatively diagnostic. It's generally a unique number for each type of pure metal you might be dealing with. So if you suspect that your metal sample is steel rather than iron, in addition to looking at its density, one thing you could do in the laboratory is determine the specific heat of the metal and see if it compares better to steel or to pure iron. So in this problem, we're going to use the calorimetry equation, once again, Q equals mc delta T. But in this case, because we know the system's mass, the heat absorbed by the sample, and the sample's temperature change, we are going to rearrange the Q equals mc delta T equation, and we are going to solve for the specific heat of the metal C. So looking at the setup for the problem, we see that the mass of the metal is 348 grams. We're going to use that for the mass. The metal piece absorbs 6.64 kilojoules of heat. So that's going to be our Q. It's a positive Q because the heat is being absorbed. But notice here that the amount of heat absorbed is given in kilojoules, not joules. And because our units in the specific heat are in joules typically, we need to convert from kilojoules to joules when we look at our heat absorbed before we start the problem. Finally, the initial temperature and the final temperature of the metal samples are given, so we have everything that we need to use the Q equals mc delta T equation. So we're going to take Q equals mc delta T, we're going to reframe the units on our Q so that it's in joules, not kilojoules, and we're going to rearrange the equation solving for the specific heat, C. So if I convert my 6.64 kilojoules to joules, remember that there are 1,000 joules in a kilojoule. So 6.64 kilojoules is 6640 joules. This is an essential conversion you have to make because the units of your specific heat, we want to be in joules at the end. So we're going to rearrange and say C equals Q divided by M delta T. We're just rearranging our equation here. Solving for C, we see that Q is 6640 joules, the mass of the sample is 348 grams, and the temperature difference is the final temperature minus the initial temperature, so delta T is equal to 43.6 minus 22.4 degrees Celsius. Crunching the numbers, we see that the specific heat of the metal is equal to 0.900 repeating joules per gram degree Celsius. So looking at our units, we have joules in the denominator, we have grams, and we have degrees Celsius we have joules in the numerator, we have grams and degrees Celsius in the denominator. So none of our units cancel, and they match the units that we would expect for a specific heat measurement, joules per gram degree Celsius. We're entitled to 3 significant figures in our answer because we have 3 significant figures in the mass, same in the heat, and the same in the temperature. So our final answer is 0.900 joules per gram degree Celsius.